Among the most cherished memories I have are those from my years in scouting. I was very fortunate to be part of an active troop that took the getting outdoors part of the scouting way very seriously, and so every month I had a chance to camp outdoors in various locations of Southern Oregon and Northern California. My favorite experiences were when we went to the mountains of the Cascade Range of stratovolcanoes because I loved the landscape, and even more, the sky. Every year, for at least a week in the summer, I would attend a summer camp at a place known as Lake of the Woods, which was nestled under the shoulders of the long-dormant Mount McLaughlin. We had a dock that jutted out from the small waterfront area that created a swimming zone, and while I loved swimming in the lake, what I loved even more, when I got the chance, was going out to the dock to look up at the nighttime sky. Far away from the lights of my small town, the stars looked like gemstones spread across a vast velvet canopy, almost close enough to touch. I loved that each star was a bit different. Some were bright and bold, while others were perfect little points of light. More astonishing was that they came in different colors. Vega was white, but Arcturus was orange, and Teres, just visible above the horizon, was as red as the planet Mars, while Pollux in the constellation of Gemini was yellow. As a young boy, I remember being amazed by it all, but as I got older and I fell in love with astronomy, I began to learn a bit more about why they were the colors they were. Some of my friends, learning of this, wondered how it was that this new, more factual, more scientific information didn't destroy my love for the beauty and romance of the stars. But for me, it only made them more wondrous. When I was in high school, I would take every chance I got to look up and remind myself where they all were. And then I went to college, and there wasn't much time for getting out and looking up. In graduate school, among the group of galactic dynamics researchers I worked with, the data often came in from huge radio telescopes, and there was a bit of pride among some that they had never looked through a telescope, nor could they locate constellations in the sky. For about 10 years, I could only steal glances upwards on a few camping trips away from the bright lights and endless research. Then I moved to the middle of the Kansas prairie to teach at a small school that was looking for someone who might be able to get their small observatory up and running again. Over the next couple of years, I became the region's astronomer, and once again, I learned the night sky. Now, though, it was the winter sky that fascinated me, with brilliantly white Sirius sitting next to Orion, with its stars ranging from blue Rigel to red Betelgeuse. There was orange Aldebaran as the eye of the bull Taurus, and the blue-white cluster of the Pleiades arrayed all across the southern sky in those cold winter months when the air was crisp and clean and the stars seemed sharp enough to cut you. All of these colors, so beautifully spread across the expanse of the heavens, drew me into astronomy. Learning what those colors taught us engaged my intellect as nothing ever had before. As I learned first of spectra, and then of the work of those who spent not just hours, but lifetimes decoding the information within them, I found myself drawn into the field of research that would challenge me to understand the most fundamental aspects of the universe in which we live. This week, we'll begin to look at that work, and as we do, I hope that your imagination will be captured, just as mine was. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 33, Seeing the Stars Anew. As spectra came to be better characterized, if not completely understood, through the work of Kirchhoff and Bunsen, an entirely new way to know things about the universe was opened up for study. As we said in our last episode, being able to determine which elements produced which absorption lines in the sun's spectrum was the major astronomical upshot of the work of the two German scientists at Heidelberg. It should be noted, however, as exciting as this was in the field of astronomical and astrophysical research, it was also a huge advance in chemistry, as it provided another way to do analysis. For those of you who have listened to our episodes on the history of the atom will recall that in our episode on the periodic atom, we discussed an early version of an elemental classification and organizational scheme similar to the eventual periodic table that relied on spectral similarities between various elements in order to group them. As you might imagine, it wasn't long before there was a shift from analyzing the solar spectrum to looking at the light coming from the stars. As we've already mentioned, as far back as Huygens, there were attempts to gather starlight and then split it with a prism. The most successful of these had been done by Fraunhofer before his life was cut short, which by the way happened at the age of 39, not 13, as I mistakenly noted in the last episode. Thanks to faithful listener Kevin N. for catching that and bringing it to my attention. While Fraunhofer was able to make a few sketches and notes regarding the characteristics of the stellar spectra he observed, the problem with these efforts was that observing these spectra with any great detail was pretty tricky. The issues more or less all stem from one big problem, and that is the lack of light. Obviously, the sun produces light in great abundance, and so the issue there was more limiting it to a small enough amount so that it doesn't overwhelm the observer. With starlight, though, the problem is the opposite. How do you gather enough light to shine through a prism so that you can actually observe features of the spectrum produced in such a way? So there are three things that are useful here. The first is better prisms that absorb less of the light incident upon them. This, however, is a lesser matter. Make better glass, get better prisms, that's something that's already well in progress. The second issue, or the second thing that you can do, is to build better telescopes, something that can manifest in two ways. The first, of course, is to build telescopes with bigger objective elements. For professional astronomers of the mid-1800s, this meant bigger objective lenses for the refracting telescopes they preferred, while for amateurs it meant bigger and more reflective mirrors for the cheaper and shorter reflecting telescopes they tended to use. And we'll return to this distinction in later episodes as it becomes important right around 1900 or so. The second part of this, though, was to develop telescope mounting systems that could more easily track the sky. One of Fraunhofer's biggest advances was actually in creating mounts for refracting telescopes that he had built that were known as equatorial mounts. As we mentioned in the episode on discovering stellar parallax, this arrangement pointed the pivot around which the telescope moved at the celestial North Pole. This allowed the telescope to be able to be pointed at a coordinate on the celestial sphere and then easily moved by rotating around that celestial North Pole pointed pivot. In time, simple motor drives would be developed that would be able to match the telescope's rotation around that pivot with that of the heavens through proper gearing, something similar to what you might see in a mechanical continuous clock drive. This would allow an astronomer to point the telescope at a single object and have it track that object as it moved across the sky through the night. Now, you may be wondering why this might be important. Well, for starters, it meant that the observer didn't have to be constantly trying to track the object and thus having to switch his attention back and forth from observing to guiding again and over. As focal lengths of telescopes become longer and thus their magnification increased, that meant that the telescope would be looking at a smaller and smaller patch of sky, which made it really convenient to be able to point the telescope at that little patch and then have it track. The bigger thing, though, had to do with this third technology we want to discuss, and that's the use of photography. Before we get into astrophotography and the revolution it will produce, I want to spend a few minutes explicitly discussing how astronomical data was being collected, why it was collected in that way, and what that meant in terms of limitations and methods. The human eye doesn't really store up light for very long before it takes whatever's been accumulated there in the retina to create a signal that is then sent via the optic nerve to the brain to be processed and acted upon. This makes a lot of sense if you're a critter living in a fast-changing world where real-time information gathering is super important for survival. However, what this means is that dim objects aren't perceived in much detail, if at all, and the images, turns out, can't be stored in a way that can be easily transmitted to, of course, another investigator. You might see the rings of Saturn, for example, but you can't just dump that image into the brain of another astronomer. For the entirety of the history of telescopic astronomy, from Galileo up to this point, if a visual record was needed, it had to be recorded through drawing. This, however, was often rather imprecise. Remember, science is best done quantitatively. Sketches of the surface of Mars are useful to a point, but they lack the desired numerical specificity that one would like to have. Thus, methods of quantifying things have to be developed, and they were developed. In the cases where the motions of objects were being observed, that was easily recorded through measuring the angles to reference points, usually other stars. This is the kind of thing that had been going on back to antiquity, and with the development of telescopic astronomy, that continued. In the cases of things where you had disks, like when you had looked at the sun or the various resolvable worlds, geographic coordinate systems were established, and features such as the positions of sunspots, the Great Red Spot of Jupiter, and the ice caps on Mars would be noted in reference to those sort of imposed geographic coordinate systems. In the case of the brightness of stars, a similar sort of comparison system was developed based on an updated version of Hipparchus's magnitude system, where 1 was the brightest star and 6 was a star you could barely see in terms of magnitude. So let's see if we can apply this to our discussion at hand. In the case of spectral analysis, this is where Fraunhofer's work was so very important. His use of a standard pair of lines created something of a reference scale in his spectra to measure wavelength from, and his notation was of those most important features in the solar spectrum would allow for specific comparison points when the spectra of other stars were observed. It's also why it's so important that Kirchhoff could use a specific spectrometer that allowed him to superimpose the spectrum of an investigated sample, say something like calcium, with the spectrum of the sun in his and Bunsen's research. This ability to compare allowed for a reproducible quantification of the observations when no sort of permanent record of them could be made. This is where photography, of course, is going to come into play. If you can take a picture, you can permanently record what it was that was observed, and that record can be shared with other researchers. And that record is really very objective in many ways. Nearly as important is the fact that the photograph can collect light over time so that the spectra of dim objects can be collected, or perhaps a better term might be accumulated. Now, I don't want to get into the history of the development of photographic technology, as I think it takes us away from the main part of our developing narrative here. But it is useful to note a few milestones to give something of a timeline as to when those technologies begin to have a significant impact on astrophysical research. The first photograph of an astronomical object was taken in 1840 by J.W. Draper when he imaged the moon using an early process known as a daguerreotype. And that's sort of an early process in which the image was produced on a silver plate sensitized to iodine and then developed in mercury vapor. Throughout the 1840s, several other images were made using this process, but they were all of fairly low quality. In 1851, a new process, known as wet collodion or wet plate photography, was developed that resulted in better images, though the preparation of the glass plate on which the images were made still took a good bit of skill. The first telescope specifically designed to photographically record astronomical observations using this method was built by the New York amateur astronomer Lewis Rutherfurd in 1856. We'll have a little bit more to say about him down the road here. In 1881, the complicated wet plate preparation technique was simplified in what is known as a dry plate technique by British and French astronomers in such a way that astrophotography moved to the forefront of astronomical data gathering techniques. As we get further into our story, especially with the work done at the Harvard Observatory, this advancement will be key to the monumental work that gets done during that time. One last technological advancement that would be made during this period of time will be something called a diffraction grating. We mentioned diffraction gratings in the last episode, and before we conclude with this introductory material, I want to make just a few comments about how they work and what their strengths and drawbacks are. A prism, as we've discussed, creates a spectrum by bending or refracting the different wavelengths of light by differing amounts. A diffraction gradient produces a spectrum in a very different way. We know that when waves encounter a barrier or an opening, they reflect off or pass through that barrier or opening in a very specific way that produces a phenomenon known as diffraction. It's a characteristic of all things that show wave behavior, including light. Now, if you have one or more of these either barriers or openings, each of them will produce a diffraction pattern for the wave that interacts with the object. Now, if these diffraction sources are fairly close together, the wave patterns that each produces will interact with the other wave patterns the other diffraction sources produce, in something that we call interference. In some places, this interference will be constructive. In other words, the wave crests will add to the wave crests, and the wave troughs will add to the wave troughs, and it'll make for bigger waves. In other places, though, the interference will be destructive. You'll get wave crests running into wave troughs, and they'll cancel each other out. Okay, so far so good, I hope. For a single wavelength of light, this would produce an alternating band of bright and dark regions on a screen on the other side of the barriers or the reflective surfaces that cause the diffraction. These bands will have a width to them. They'll have a sort of thickness on the screen, as it were. The more reflection sites from the diffraction source you have, the narrower those bright bands will be. Also, their position will be determined by both the wavelength of light and the spacing between the reflection points on the diffraction source. This is how Young was able to determine the wavelengths of various colors of light, as we discussed in the last episode. Now let's say you shine white light in at your diffraction source. Each of the different colors will add together at slightly different angles, and so you get constructive interference for the different colors over a range, and that's what creates your spectrum. The more reflection sources you have, the more precise this process will be, and the more accurate and not smeared out, in a sense, that spectrum will be. The caveat to all of this is that for this diffraction method of creating a spectrum to work, the diffraction sources all have to have the same distance apart, or spacing as we call it, from each other. While this could be done for 2 or 3 reflection sites, it was really very difficult to do accurately for a large number until Henry A. Rowland at Johns Hopkins University invented a machine that could very precisely etch hundreds and then later thousands of lines per inch on a glass plate, all of them with exactly the same spacing. Each of these lines would act as a reflection source, and so extraordinarily accurate spectra could be produced. And by accurate here, what I mean is that each wavelength of light would constructively interfere only at a very precise angle. Actually, and this is kind of interesting, the way the math in this all works out is there are actually multiple precise angles at which each wavelength will be produced. And each of those angles is a multiple integer of the previous angle. So, if red light with a wavelength of, say, 650 nanometers constructively interferes at an angle of exactly 10 degrees for a given diffraction grating, then this will also happen at angles of 20 and 30 and 40, etc. These are known as higher order diffraction spectra, and what's really great about them is that they spread out the spectral features for a more minute measurement. This, however, is also kind of the drawback of a diffraction grating. In a prism, while some of the light is absorbed by the glass, most of it goes into making a single spectrum that's relatively bright. For diffraction gratings, though, much of the light is canceled out, and that which isn't is spread out over multiple orders, thus making each individual spectrum dimmer. While this certainly isn't really an issue with the sun or another bright source like the moon or even Venus, it will be an issue for getting the spectra of the stars. When developed in the 1880s, diffraction gradient spectrometers will require large telescopes to be truly effective astronomical tools, thus spurring a drive for bigger and bigger instruments that will fundamentally alter the trajectory of telescope technology after 1900. Okay, with some of the technological and technical aspects out of the way, let's get into the story of those astronomers who began to collect spectra and then draw conclusions from them. Following Fraunhofer's single paper on the spectra of bright stars Sirius, Castor, Pollux, Capella, Betelgeuse, and Procyon, published in 1923, there was a nearly 40-year gap before anyone tried to do any significantly quantitative work in stellar spectroscopy. While astronomers like Johann von Lamont and William Swan seemed to dabble in the subject, their publications did little to add new knowledge. It wasn't until the Italian astronomer Giovanni Battista Donati, working in Florence since 1860, that things began to pick up. He published the spectra of some 15 stars, drawn in great detail. While most of these stars shared a common feature in having a strong absorption line in the blue-green part of the spectrum, his other measurements would be found to be questionable by later investigators. Nevertheless, his 1863 paper on the subject in the monthly notices of the Royal Astronomical Society marked a significant turn towards the recognition that spectroscopy offered the promise of real scientific advancement in the understanding of the stars. This is very likely due to the publication of Kirchhoff and Bunsen's work identifying the presence of specific chemical elements as the cause of particular absorption lines in the solar spectrum. In that same year, 4 men independently set out to more systematically expand on Donati's work and attempt to create a classification scheme. They were the American amateur astronomer by the name of Lewis Rutherfurd, the British Astronomer Royal George Airy, amateur astronomer William Huggins, and an astronomer and priest by the name of Angelo Secchi, working at the Collegio Romano. While there has been some historical bickering as to who among these 4 was the first to take up these more systematic observations, it seems fairly clear to me that, inspired by the work of Kirchhoff and Bunsen, as well as Donati, each embarked on their course of investigation more or less independently of the others. What is most important here is that each of these men went beyond the mere collection of stellar spectra to attempting to arrive at some kind of organizing principle with which to better understand them. As we've said in other episodes, this is an important step in developing scientific knowledge. Let's take a look at each in turn, beginning with Lewis Rutherfurd. Rutherfurd was a New York-born, Massachusetts lawyer whose grandfather had been a U.S. Senator and great-grandfather had signed the American Declaration of Independence. He had earned his law degree at Williams College in Massachusetts in 1834 and had practiced for about 15 years before giving up the profession to pursue his interest in science. From 1849 onwards, after having returned to New York and setting up his own observatory facilities, he made a number of contributions to moving the technology associated with astrophotography forward, including, as we noted, developing the first telescope specifically designed for photography. In 1862, he began making observations of stellar spectra and soon published his work in Stillman's American Journal, writing, quote, "The star spectra present such variety that it is difficult to point out any mode of classification. For the present, I divide them into 3 groups. First, those having many lines and bands, and most nearly resembling the sun, viz. Capella, Beta Geminorum, Alpha Orionis, Aldebaran, Gamma Leonis, Arcturus, and Beta Pegasi. These are all reddish or golden stars. The second group, of which Sirius is the type, presents spectra wholly unlike that of the sun, and are white stars. The third group, comprising Alpha Virginis, Rigel, etc., are also white stars but show no lines. Perhaps they contain no mineral substance or are incandescent without flame." End quote. In this quote, we find the first attempt to group stars into different categories based on characteristics of their relative spectra. While Rutherfurd was hampered by the low resolution of his instrument, based on an early diffraction gradient, especially in making out the features of his third group of spectra, this classification scheme became the basis for almost every subsequent discussion. One final note of interest regarding Rutherfurd is that he was known as the greatest lunar photographer of his era, and his images of the Earth's largest natural satellite graced the covers and frontispieces of many an astronomical work for years to come. The next work we wish to consider is that done in Greenwich, England by George Airy and his assistant, one Mr. Carpenter. Airy is one of those mid-19th century scientific figures who worked on what seemed like everything, or at least everything in physics. When he was appointed Astronomer Royal in 1835, the Royal Observatory had more or less fallen on some pretty hard times. While observations had continued, they were rarely reduced to give meaningful data, and the instruments had not really been updated from the time of Herschel. With great energy, Airy set out to work in order to put things right, and by 1860 several new instruments had been installed, the backlog of observations had been cleared, and new research was being conducted. In 1863, Airy and Carpenter instituted a small survey of stellar spectra that looked at 19 bright stars and recorded the positions of some of the more prominent spectral lines. While the work was admittedly crude, it would form the foundation of a much more significant effort that would commence in 1868, that of measuring the shifts in spectral lines due to a star's motion either towards or away from the Earth due to the Doppler effect. Combined with the measurement of proper motion, this would allow astronomers to arrive at a true three-dimensional understanding of a star's relative motion with respect to the Sun. The third figure in this discussion is Father Angelo Secchi. Born in 1818, Secchi had trained in the Jesuit order, which he entered at the age of 16. He continued his studies at the Collegio Romano, showing a real talent for physics and mathematics, and in 1839 he was appointed a tutor at the college. 2 years later, he was elevated into a full professorship where he taught for the next 7 years. In 1847, he was ordained a priest, but just a year later, the Jesuits were expelled from Rome as part of what is known as the Roman Revolution, one of many such uprisings in 1848. He then traveled first to England and then the United States, where he taught physics and astronomy at Georgetown University, where he earned his doctorate in theology and began working with the first director of the U.S. Naval Observatory, Matthew Fontaine Maury. In 1850, he returned to Rome, and 2 years later, with the support of Pope Pius IX, he moved the college's crumbling observatory to a new location atop the chapel of the college and undertook a truly ambitious research program. Like Airy, his contributions to astronomy are legion, including work with double stars, some of the earliest observation of Mars' surface, and a great deal of work in observing and characterizing the Sun's atmosphere, leading to the development of new instruments for studying the Sun and the discovery of what are known as spicules, a transition feature between the Sun's photosphere and chromosphere. His true passion, however, was spectroscopy, and in addition to a great deal of work on solar spectroscopy, he initiated the first large-scale survey of stellar spectra. Over time, he would collect some 4,000 spectra, which led him to propose an improvement on Rutherfurd's classification scheme. In 1866, he put forward 3 classification categories. The first, blue stars such as Sirius and Vega, which show broad absorption bands in the blue and violet portions of the spectrum. As you might expect, these were labeled Class 1 stars. The second group were white stars with very fine or very thin absorption lines such as Arcturus, Procyon, and Capella. These were designated Class 2 stars and were seen to have spectra very similar to that of the Sun. His third group were colored stars such as Antares, Alpha Ursa Majoris, and Alpha Orionis, which displayed wide absorption bands in their spectra. These he called Class 3 stars. 2 years later, in 1868, as more data poured in, Secchi added a fourth category that included very faint red stars whose spectra was different than the Class 3 stars, even as they were similarly colored red and orange. These he called carbon stars due to their strong spectral lines corresponding to the laboratory spectrum of that element. Finally, in 1877, he would add a fifth classification with stars that displayed not only absorption lines, but also emission lines in their spectra. He would die a year later, leaving behind as rich and varied a scientific legacy as anyone of his generation. The final figure of our four is William Huggins. Born in 1824, Huggins was a lifelong amateur astronomer in the sense that he never occupied a paid position in doing his astronomical work, nor does it seem that he ever received any sort of formal university training in the sciences. I've not been able to find any sort of reference to what he did for the first 32 years of his life other than to attend the City School of London. But in 1856, he built his own private observatory using his own funds. 6 years later, with the help of his friend and professor of chemistry at King's College in London, William Allen Miller, he began making spectroscopic observations of various astronomical objects. While he certainly did make stellar measurements at this time, his more novel contributions were to examine the spectra of Herschel's planetary nebulae, as well as that of two nova that occurred in the 1860s, as well as that of a comet. What is most notable about Huggins' measurements was that he specifically worked to match the spectral lines he observed with the bright line emission spectra Kirchhoff had documented for each element, and thus began a chemical analysis of each of the objects he studied. This is seen by many historians of science as the true birth of stellar astrophysics, wherein the compositions and the temperatures of the stars were first probed. While this would have been a notable body of work, Huggins had a second act to come. In 1875, at the age of 51, he met and married Margaret Lindsay Murray, a woman 24 years his junior. Murray had a keen interest in astronomy and stayed abreast of the latest advances in both telescopic and photographic technology. Their marriage truly represented a real meeting of the minds, and she began to push Huggins to use new photographic techniques that would result in some of the first photographs of spectra of both stars and comets. The two of them would work closely together and would publish a number of works until 1910 when William passed away. Margaret would remain active in research until her death 5 years later. She would be known as the Herschel of spectroscopy for her work in producing photographic spectra of many different objects. In the 1870s, the Huggins weren't the only ones beginning to work with photographic techniques to record their spectra. In the United States, the physician Henry Draper had taken up astronomy. He came to astronomy through the work of his father, John William Draper, who we've already talked about as being the first guy to photograph the moon in 1840. In 1872, he placed a quartz prism in front of the focus of his 28-inch reflecting telescope at his private Hastings-on-the-Hudson observatory and made a photograph of the spectrum of Vega. In it, he was the first to record a series of strong, dark absorption lines, most likely due to hydrogen. So successful was this endeavor that he resigned his position as chair of the New York University School of Medicine to devote his full-time energy to astrophotography. In 1874, he directed an expedition to photograph a transit of Venus, and in 1880 he took the first photographs of the Orion Nebula, as well as recording for the first time the spectrum of Jupiter. What he had mastered was the art of both understanding how to do astrophotography with the still unfolding technologies there, as well as guiding his telescope accurately enough to get good, long exposure pictures of various objects and spectra. He seemed to be on the cusp of a truly brilliant astronomical career when his life was tragically cut short in 1882 due to an undiagnosed infection of the tissue around his lungs. His role in our story, however, is far from over. As we will see in a future episode, his legacy will be assured by the generosity of his widow, who sought to have his work carried on. At about the same time, Hermann Carr Vogel was taking up the work that was very similar to that of Secchi. Vogel is somewhat unique in our story here in being one of the few professionally trained astronomers to work in spectroscopy at this time. He had earned his doctorate in 1870. Working first in Kiel and at a private observatory there, and then later at Potsdam, Vogel did a great deal of work to catalog the wavelength of some 2,600 lines in the solar spectrum, which is a truly monumental work. He then undertook a survey of the spectra of all stars in the band of the sky near the ecliptic down to magnitude 4.5, which is just a little bit brighter than the limit of human seeing. While this survey was never truly completed, he did collect enough data to develop his own spectral classification scheme that resembled Secchi's, but that placed a greater emphasis on the understanding that a star's evolution through various states would have on those developing or those changes in the spectra. We'll return to this idea momentarily. Over the course of the next 3 decades, Vogel would perfect the process of making detailed photographs of stellar spectra and then measuring the shifts in the spectral lines to determine the velocities of the stars, that Doppler effect thing that we were talking about earlier. He first applied this method to the spectral lines of the Sun, taken from different parts of the edges of the Sun's disks, in order to more precisely determine the Sun's rotation. To get an idea of how this works, what I want you to think about is, think of a ball, like a tennis ball or something, rotating on its axis. One edge of the ball moving towards you and the other edge moving away. Now, if you're standing far enough away, and let's say that ball's pretty solid, you're not going to really be able to tell how fast it's rotating, unless you can find another way than just looking at the ball itself. What Vogel did was take a spectrum of the Sun on each side. Think of the Sun like being that tennis ball, right? And then he measured the shift in the Fraunhofer spectral lines to determine what the velocity of each edge of the Sun was via that application of the Doppler effect formulas. By doing this, he was able to confirm that the Sun didn't rotate as a solid body, but rather with different rates at the equator and at the poles. Something that people already knew about by looking at sunspot rotation rates, but this gave a direct physical measurement of that. Vogel made a number of other important contributions that are either a bit too technical to go into here, or that will be better considered in later episodes when they make more sense in the context of what will be discussed there. As such, we will leave his observational work for the time. One useful note, though, is that it was Vogel who first confirmed Norman Lockyer's claim of a new element in the spectrum of the Sun. This discovery would cause Vogel to re-examine the spectra of many of his stars, thus leading to a recognition of helium being present in many, many other stars. This, of course, required Vogel to reevaluate his classification scheme, and so, in the late 1890s, the idea of stellar classification was once again in flux. At this point, it is useful for us to spend just a little bit of time talking about where all of this new data was leading. One of the reasons you collect a lot of data and then create an organizational framework to place it in is to try to see if there are any revealed patterns that will give you insight into the underlying physical reality that gives rise to that organizational classification. As the stellar classification schemes of first Rutherfurd, and then Secchi, and finally Vogel were being considered, many astronomers began to look to see if they could develop an evolutionary life cycle for stars. By this time, it was thought that stars would form, go through some sort of set of processes, and then end their lives in some fashion, an idea that dated all the way back to the writings of William Herschel. What wasn't understood was what that process actually was. The other thing that needs to be recognized in this conversation is that during the 19th century, any hypothetical models only had the physics of thermodynamics to work with. Things like atomic physics hadn't been discovered, as we don't yet have, what we would call sort of a nuclear model of the atom to work with by this point. In this framework, based on thermodynamics, gases got hot when they were compressed, and then would cool as they radiated that energy away as light. This would cause the gases to take up less space unless a new source of energy was added to the gas. The earliest attempt to put forward an evolutionary process dates to about 1865, when J.K.F. Zollner at Leipzig put forward the idea that stars start off as planetary nebulae, which then contract and cool to form liquid spheres with a solid crust. These, therefore, are blue stars, as they'll be very hot. And then, as they cool, they fracture every so often sort of to release hot liquid, creating variability in the brightness of the stars, something that was observed in several cases. After a time, these stars would then stabilize and change color as they cooled from blue to yellow to red. Here, therefore, blue stars were thought to be the youngest, while red would be the oldest stars. And a star would evolve through the various types of spectra that had been classified by those earlier investigators. Over the next 25 years, these ideas would be modified and expanded upon until the next big step was taken. The most prominent among those proposing a type of evolutionary process in the 1890s was Norman Lockyer, but he built on that previous idea by adding an important phase to the process. Like many in our story, Lockyer was an amateur astronomer with no formal training in any scientific discipline. What he did have was an enormous capacity for hard work and a flamboyance that made him one of the earliest modern popularizers of science. Lockyer got involved in stellar spectroscopy a bit late in the game, in 1890, but soon the subject was both fascinating to him, and he found that there was a need of a narrative that told how stars came to be and what their ultimate fate would become. In service to this end, Lockyer created his own stellar spectra classification scheme that derived as much from his assumed evolutionary track as it did from any data. In other words, he had a tendency to fit his spectral data to support his evolutionary model, not the other way around. In describing Lockyer's model, let me turn to the words of John B. Hershaw, whose book, The Analysis of Starlight, serves as a valuable, if a bit technical, source for this episode, and that will also be the case for many of our episodes in the future. He writes, quote, "The basis for Lockyer's spectral classification was to support his theory of stellar evolution known as the Meteorite Hypothesis. The universe was supposed to be full of meteorites which, on colliding, were heated and vaporized, giving first gaseous nebulae or comets. These vapors of these bodies then condensed to form young stars which contracted to give a rise in their surface temperature. Eventually, the loss due to radiation, and here he means the radiation of light, from the star was just balanced by heating due to contraction, at which point the stars were at their highest temperatures. Thereafter, the life of the star entered a prolonged phase of cooling, ending in final extinction. At any given temperature, there were therefore stars on ascending and descending branches corresponding to objects of increasing and decreasing temperatures." End quote. So, to sort of break that out a little bit, for Lockyer's scheme, the various stellar colors were indicative of which part of the evolutionary process the star was on. Red stars with emission lines were still collapsing from the parent vaporous materials. Hot blue stars had finished their collapse and were as hot as they were going to get. They then descended through the classifications of white, yellow, orange, and then again red until they stopped producing light altogether. While Lockyer's narrative was compelling, especially in that it seemed to mirror the life cycles of many organisms seen on the Earth, his support was, well, shaky to say the least. As Hershaw notes, many of his claims that were published at the time fell far short of what would be considered scientific evidence today. Still, the model did seem to follow the generally accepted thermodynamic processes, and those parts associated with the collapse phase of the process actually match up surprisingly well with the models of star formation based on the data that we have. One important feature of Lockyer's model was that all stars, regardless of size or mass, would follow the same evolutionary path. Over time, a bit of a schism would develop in the astrophysical community as to which model was more likely to be correct: Zollner's blue, yellow, red progression, or Lockyer's blue or red, blue, red sequence. It is interesting to note that William Thomson, aka Lord Kelvin, which has to be like the coolest name in science, don't you think? And Hermann von Helmholtz developed a robust physical model of the source of the sun's energy based on these sorts of thermodynamic collapse considerations. Beginning with conservation of energy, it is possible to determine how long the sun could produce light at its present rate by converting gravitational potential energy into radiant light energy through collapse. The calculation, when you do it, comes up with a number of approximately 9 million years, which, when viewed through the biblical age framework common in much of Victorian England at the time, seemed like a more than reasonable number. However, not long after their results were published, evidence began to accumulate from geological and biological investigations that supported an idea of an Earth that was at least 1 billion years old. The Kelvin-Helmholtz luminosity equation, as it's called, was not discarded, however, as it proves to actually be a really excellent model for what we now call the initial collapse of a protostar. For me personally, it was the master of this derivation in my first astrophysics class that gave me the confidence in grad school that I might actually be able to do this whole astrophysics thing. It is at this point that I think we've probably reached a good place to bring this episode to a close. I apologize for the somewhat shorter length of the show, but as I mentioned previously, this week was finals week, and I spent a good bit of it giving and grading my finals, and so my research in preparation for this episode has been just a bit limited. There are, however, a couple of closing comments I would like to make. As today is Mother's Day here in the U.S., I'd like to devote my weekly shout-out to all of the moms out there who are part of the crew of the Odyssey. My own mom passed away a few years back, but it was her encouragement of my inquisitiveness and creativity that made a path in the sciences for me possible. While I know she wanted me to go into law, she was the one that made sure that when I was 13 and Carl Sagan's Cosmos came on, I had unrestricted access to the TV for that 1 hour a week, much to the chagrin of my younger brother who wanted to watch another of those seemingly interminable Three's Company reruns. When, in 1984, I wrote my high school senior research paper on stellar evolution, she was the one who liberated the IBM Selectric typewriter from the office of the attorney she worked for so I would be able to produce the 28-page, heavily sourced monstrosity that would both baffle and thrill my English teacher, Miss Frostad. So this evening, I will take a few moments to raise a glass to her memory and give thanks that I was lucky enough to have a mom who encouraged my scientific interests. I hope all of you can do the same. Today also marks the 1-year anniversary of my being run over by that 18-wheel truck. I'm planning to ride a bit later today out to the site to take a few minutes to consider how lucky I am to have not only survived, but to have had a somewhat miraculous recovery. While I still struggle with pain every day, and I have a ways to go to get back to where I was, I can see that place from where I'm standing now. Thanks to the kindness of those strangers who stopped traffic on the road where I was hit, the excellent and quick work to the Pike County EMS personnel, and the amazing doctors, nurses, and medical staff at Grady Memorial Hospital, I actually have a pretty good chance at a reasonably normal life. While I expect that the rods in my back will always remind me of the changing weather, the fact that I can still ride my bike the 30 or so miles it'll take to visit that location is nothing short of incredible. Finally, as I'm taking a bit of a vacation this coming week, the release of our next episode might be delayed just a bit. While it is possible that I'll be able to release that episode on Sunday night of next week, it's more than likely that I'll have to get something up on Monday. Unless, of course, I pack all of my recording gear and try to do all of that stuff up in the mountains of North Carolina. Either way, you'll hear from me again soon. No 2-week break yet for a while. In that episode, we'll continue our discussion of stellar classification, but rather than jumping around from place to place, we'll travel to Cambridge, Massachusetts, and meet with an extraordinary group of people whose work would forever change how we understood our place in the universe. Until then, full sails on your journey.